So I'd like to welcome to the stage Beth Fitzpatrick, who's here to talk about quantum systems engineering. What could it become, and why should today's systems engineers care?
Thank you very much, Andrew. I tell you what, that was a really exciting talk. I almost forgot I was about to get up and speak myself then, so really interesting to hear that talk. So thank you so much for that warm welcome, and lovely to be at ASEC today. I'm here without my co-author, but I'm going to do a little bit of a talk today about the paper that we've written together, which, as Andrew introduced, is all about quantum systems engineering. So the purpose of the talk is not going to be a quantum 101. It is not going to be giving you guys that detailed information about quantum. Firstly, I am way underqualified for doing that. That is Mark, my co-author's role on the team. But what I am going to do is hopefully get rid of any fear that you might have. It is not scary. But quantum revolution is incoming. It's already started and it's on its way. So that little ghost emoji there, it's nothing to be afraid of. That is really the number one objective of my talk today. Secondly, so what? Okay, what is the opportunities? What are the risks? What are the weaknesses, strengths, and threats of this quantum thing that's coming? And why should we care? Why should you guys, as systems engineers, care about this incoming kind of quantum revolution on its way? And a challenge, really looking at the theme that we've started already this morning in those emerging new opportunities. How can you engage, both as individuals, both as companies that you're part of the community that we're a part of here at ASEC 2023? How can you engage? So it's not going to be all quantum. Do not fear. Do not feel like you're going to have to go away with your head hurting too much. So who are the authors of this paper? So that's me, Beth Fitzpatrick. I'm a consultant at Atkins Realis. I've got experience across kind of security, defence and technology kind of sectors. And I studied an undergraduate master's in physics. So that's my background. I've done a whole host of different training kind of in my industrial career, whether that's from kind of architecture to requirements, a whole host of different bits and bobs, including data science. Really that bottom bit, that key bit as well, is the real skills aspect. So I'm really passionate about ensuring that we have the right people involved in creating the next generation of people, whether that be through solving the climate crisis. As we know, systems engineers are really desperately needed in that, and an ambassador and a mentor as well. And there's a bit of a skills overarching piece that you'll hopefully get from this talk, and that call to engage across the board. And my co-author, who's unfortunately not here today, is Dr. Mark Everett, and he is the Director of Studies at Loughborough University. So that's the university that I studied at. I reconnected with Mark just over a year ago. I was invited to an industrial advisory board, and since then I've been working with Loughborough University in that visiting fellowship position. It's really, really interesting. Hopefully I'll give you a little bit of an insight into that. And again, it's another potential opportunity for you guys to engage potentially. And he is that quantum scrap to the team. So to baseline everyone, to get everyone up to speed, to make you feel like you're not going to be completely out of your depth, I'm going to just flash this one up on the screen. So raise your hand if you've seen this graph before or you've heard of a technology readiness level. Brilliant. Yeah, that's great. So the purpose of bringing this up is to really make sure we're all on the same page and to make you feel like actually you do know quite a lot about this whole industry, academia, landscape, essentially. And this isn't quantum specific. This is across all technology, all innovations. And what this kind of graph shows, it was developed by NASA, kind of made popular in the 1970s, is it gives a little bit of a common taxonomy and understanding of where technologies, innovations, capabilities are. So starting in that bottom technology readiness level, TRL level, so that is kind of new ideas, new thinking, what's possible, all the way going up to where industry are interested. So that's where we are almost looking to be able to make money from something. This is where we understand the details of what's going on in the technology a little bit more, a little bit better. And there's a gap there in that middle bit. And this graph actually kind of has it represented as investment, as in money. But I think we all know and all have a pretty implicit understanding that actually it's not necessarily money that's the blocker. It's things like integratability, it's things like reliability, it's safety, it's assurance. And the challenge that I'm going to talk to you about today with that quantum lens is how we can do more as a communities, between the academic community and, for example, our systems engineering community to help bridge that valley of death, to help collaborate across our two communities to do kind of better overall, so improving the academic kind of way of working and also improving the outputs, the technologies, the capabilities that we're going to so desperately need to get to where we need to get to in terms of the climate crisis and all those big problems that we know we need to be solving as a society. So, first thing I'm going to take you through today, and this is where I'm going to come back to this one a little bit, because the first thing is a little bit about quantum. So, at very small scales, very, very, very small scales, and in some exotic states of matter, the behaviour that we can see is not what we would traditionally expect. It does not obey classical mechanics. It does not behave in a way that we would be looking at. And basically, the fundamental message is it is weird. It is weird, and it is not what we would particularly describe in mathematics. But the thing to not be really afraid of is that the maths itself is linear. So instead of using a kind of whole numbers, we're using a state vector, so in two kind of dimensions. It's Hilbert space dimensions, that's where the space that vector is in. And if you think about two waves in a classical sense, and they are interacting with each other, you can do some maths to understand what those two waves that interacted came to, how they interfered. And it's kind of similar maths when we're talking about understanding kind of quantum mechanics, but at a much bigger scale. So the maths is exponential. So you can do those simultaneous type equations with lots of variables, and that will give you the answer to that quantum mechanical equation. So the maths itself is relatively simple, but the so what is the really, really interesting bit and exciting bit. The measurement problem in particular relates to one of the two key kind of quantum tools really that we use, and that's superposition. Superposition is the fact that we are measuring in that quantum space. It's not a classical 1 and it's not a classical 0. It's a superposition of both of those numbers at the same time. And that superposition can collapse. It can be decohered. It's very sensitive to external environment implications. So that measurement problem is an open problem. So that, we're talking about some mainly low TRL technologies at the moment going into that higher TRL. But the really exciting bit is that second tool that we use in quantum mechanics to do really fun stuff, and that is that non-locality. So there are some great resources online to kind of understand the journey, the history of quantum mechanics, from thinking that light was a wave to thinking it's a particle to realising actually we have no idea what's going on. And non-locality is that really weird bit that Einstein called kind of spooky action at a distance. And that is because of something called entanglement. And entanglement is when you can't, once two particles are entangled, they're basically linked in a way that we don't really understand. And you can't actually fundamentally separate these two particles once they've been entangled in a way that we're still working out exactly how. If I just go back 2 slides, the message of this slide is fundamentally that we can see entanglement. We can see quantum weirdness. The Nobel Prize in 2022 was won by someone who kind of showed that really measurable entanglement. So it's not just quantum weirdness. It is measurable, it is experimental, we can see it, and actually we can look at starting to use it. There's a little bit of a hint here on the bottom about how we might use it, about so what, about what we can do with this quantum technologies and with the opportunities that we can do. And really, a lot of those opportunities are linked to the fragility of quantum. So the nature in which environmental aspects are really, really important in understanding, but also actually pose a real big problem in how we leverage this quantum weirdness, these quantum technologies. So it wouldn't be a systems engineering talk without a basic systems engineering tool. So I'm going to let you have about 10 seconds to think what might go on here out of what I've told you. I've given you a few hints. I've given you a few tips. I'm not going to ask for hands. Don't worry. So what have we got in this SWOT analysis? A couple of really big hitters that kind of cross across some of these strengths and weaknesses and opportunities and threats. So first one that you might have heard of is quantum computers. So quantum computers. Traditional computer, you have a bit that's either a 1 or a 0. a quantum computer used a qubit, a quantum bit, and that qubit is a superposition of 1 and 0. So it's not just a single information point. It has the ability to have a lot more information in that. And then when you entangle two of these quantum bits, two of these qubits, that gives you a quantum gate. And that can allow you to essentially do the normal computing that we might want to be doing, but actually at much larger scales. Because the capacity to have information inside of these qubits is much bigger than traditional quantum computers, normal computers. But it's not as straightforward as a normal computer is, because the properties that we're talking about, that superposition that can decohere really quickly, and that entanglement that we're trying to do between these qubits, it's really quite fragile. And environmental effects can really make it hard, really hard work to have this quantumness happening for a long enough period of time that we can do the calculations that we want to do. So this year, IBM have got a quantum computer of just over 1,100 qubits. It has to be down to the millikelvin temperatures. It's really an engineering challenge that we're up against to try and get these quantum computers to be working. So that's a strength, that's a possibility of really high compute power, and in particular, parallel processing. And that's where there's a threat. But it's also an opportunity, right? So that parallel processing has the opportunity to do large sums, in particular sums like prime numbers of very big numbers, which is actually how a lot of our encryption methods are based on at the moment. So a lot of our encryption methods that we use, particularly on the internet, is reliant on really big calculations that we wouldn't be able to solve with any normal timescale. But quantum computers, with that parallel processing, with the exponential ability to have information processing, that gives us the opportunity to solve those types of mathematics really quickly. So that is a threat to national security. There's the potential for malicious actors already, right now, doing harvesting data that's encrypted, so that when a quantum computer comes along, they can decrypt it later. So that is a real threat to national security, right now, if we're using those algorithms that can be, beaten essentially when a quantum computer comes along. So that's a threat there, that cracking of quantum of encryption methods. There is an opportunity when it comes to quantum encryption as well, though. So that entanglement, you can't copy entanglement, you can't add or take away from entanglement once entanglement's there. So that's an opportunity for new encryption methods. And I quite like the challenge as well of having, needing to rethink our encryption methods, needing to rethink the way that we've relied on doing things for the last long period of time since the internet's been here. So that is, the cryptography element. The final one, the final opportunity, and is kind of why it's so tricky to do this quantumness, is that sensing opportunity. There is some really interesting work going on at the moment, particularly in quantum mechanics. They're coming to this realization across lots of different industries that quantum is actually involved in lots of different processes. They think that quantum is how enzymes work, for example. They've also realized that quantum is how birds navigate across the globe because they pick up magnetic field changes. And that's the sensing opportunities in particular that we can look at leveraging. So position, navigation and timing, PNT, that is another real opportunity in leveraging the sensitivity, being able to pick up really tiny changes in field. That has the potential to be giving us those new position and navigation timing capabilities that's not reliant on global positioning systems. So you're not relying on having to have access to a satellite in the sky to know exactly where you are, where you're going, what time it is, and how far you've moved from where you've last been. So that's the opportunities. I think I've covered off everything on that slide. Really, it's leveraging the sensitivity. It's leveraging the capacity of that parallel processing piece and mitigating those threats as well that come through. Okay, so why should you guys care? Well, the reason why you guys should care is because it's a really exciting field to get into, because we don't know whether or not our traditional systems engineering processes are going to work. When you've got environment that really is intricately involved with the way that the tool itself works, it really throws up questions that we don't know we've got the answers to. And that includes things like system boundaries. If you've got entangled particles that are millions of miles away from each other, how do you define that system boundary really practically? Engineering for reliability, maintainability, how do we know that we can integrate this type of thing when it's so essentially fragile? And that hierarchical modelling is a real challenge that needs to be worked through, really, before we can start looking at integrating these types of technologies. How are we going to know how to assure them? How are we going to know that they're going to be safe and secure with everything else that we use in our day-to-day life? You might be sitting there thinking, hang on, but don't we already have some quantum? Don't we have kind of quantum in our mobile phones and in cameras and that type of thing? And yes, absolutely we do. But that's the difference really between the quantum kind of 1.0 that's kind of already been and gone and this incoming 2.0 kind of quantum revolution that's on its way. And the difference there is that we're leveraging that weirdness, that quantumness of entanglement and superposition. Traditional quantum that we've seen so far is things like kind of field effect transistors, so that's at the really small level. And actually, the quantumness is packaged up very small there. At a component level, we can use classical modelling. We can use all those other tools that we already have, that we've already refined, that we already know work at a component level, and we can use that classical engineering. And that is not the case when we're looking at leveraging entanglement and superposition. We don't know if we can abstract these new technologies to use our systems engineering tools at that kind of TRL6 level. We just don't know. When these quantum technologies go moving up that technology readiness levels, we don't know how we're going to be able to assure them and essentially bring that systems engineering rigor that we're going to need to operationalise and to productionise. We really don't know whether or not it's going to be suitable. So, okay, this is a bit about systems engineering. That's a bit about us. What about academia? Have they heard of quantum systems engineering? Are they already doing it? Do they already do systems engineering? Well, not really too much, to be honest. So it's relatively new. The term quantum systems engineering was first used approximately 2014, kind of looking at how we can operationalise quantum technologies and what the differences might be. So it's relatively new. It's relatively kind of young. And often there's a bit of misconception when you say systems engineering broadly within academia. They might think that it's an engineered system rather than applying systems thinking. We've had several papers at ASEC around academia at large and how we can embed systems thinking into upskilling all of our workforce, not only in engineering but in other subjects as well. And again, there's that kind of misunderstanding around what actually systems engineering is. Often people in academia kind of confuse it with entrepreneurship, with actually having to operationalise a product, which of course is one angle, but there's a huge amount of benefit that you can get from using systems engineering tools when you're understanding a really complex problem. And a lot of academic research is understanding complex problems in exactly the same way that we're solving complex problems in industry. But there are some really good things already happening. And if you do get a chance to look at our paper, there's some brilliant references in there. So there's already examples of people using, in particular, model-based systems engineering. There's a lot of interest in using MBSE. So they've used it, for example, to look at solar cells. They've used it to look at kind of quantum software architecture as well. So there was interest there. MBSE is also a really, really interesting one, though, because if you think about that scale element of quantum, that exponential piece, again, how do you model really large exponential values when you've got qubits that have that exponential kind of stacking capacity? Sometimes you might even need to use a supercomputer to model a basic quantum system. How are we going to solve this? How are we going to understand and be able to codify the work that we do in quantum in a way that's going to be reputable in an industry context? It's a real big question mark. It's a real big challenge. It's a really exciting opportunity that we really need to start looking to embrace. But there's been, other research done, and also if we look at how academics do study as well, there's been a thesis that looks at essentially doing a bit of a case study of if we give PhD students systems engineering training, what do they find useful? What do they pick up? What helps accelerate the progress of their projects? And some really interesting and not necessarily surprising results. So in particular using functional mode effects analysis, functional failure mode effects analysis, FMEA, that actually was found to be a really, really useful tool when trying to understand and work out why is my experimentation not working, why is my research not working. And also codifying requirements and just looking at that broader sense of what is it that we're trying to achieve with this project. So really lots of opportunities, and in particular that training is through the CDT, so the Centre for Doctoral Training. So there is a bit of a shift really, and a bit of a a shift between academics looking at systems engineering being a really, really useful tool and looking at how we can embed it, in particular into those PhD students who are spending a whole host of time kind of trying to understand a real technical, complex problem. How can systems engineering help, and how can we give them the tools that we know work really well? How can we train them and give them that empowered skill set to knowledge and also community to grow those skills and utilise them? So in practice, though, the focus has been, so quantum aside, the focus has kind of been on those traditional system engineering tools. There's a paper that I also reference in the paper, which is about kind of comparing the life cycle. Really, really interesting paper to take a look at there. But to be honest, the majority of interest is really in the system integrator space, in big defence companies, rather than in academic institutions. So it's a real good opportunity, to come to ASEC like this today and engage with these different stakeholders and challenge and empower you guys to go out to your communities and spread the message of the new opportunities that we've got. But what about in the other direction then? How do we join together and create this magic of systems engineering? So there's a couple of really great opportunities. One of them is, as we've already heard from today, the Adventure of Systems Engineering course. There's lots of brilliant work that's being done to help improve the training of systems engineering and make it a more diverse kind of training set that we can all go out and use and share. So that is relevant to whether that's kind of primary school children. So I recently did a STEM event where we did a Moscow analysis with a group of school children. It actually worked incredibly well. There's lots of different examples that we can use that you can apply, for example, a Moscow analysis too, to bring it to life. But also on the other end of the spectrum, you've got some schemes like the Royal Academy of Engineering. So last year at ASEC, actually, there was a paper around a systems-led approach where systems engineers were essentially supporting engineering courses, helping give them a systems kind of industrial perspective, getting them excited and letting them know kind of what systems engineering is. So there's a couple of schemes that are potentials to be involved in. And it's about joining up that push and that pull from technology, that it's not just academics coming up with something that they absolutely love and then kind of pushing it out across that valley of death, and then us engineers on the other side waiting for something to pull through. It's about joining up. It's about working together and collaborating fundamentally into a way that's going to benefit everyone. So there's a few challenges from today that Mark and I would like to kind of put to you guys today. On the quantum side, I think the challenge is about kind of codifying a common set of language, particularly around quantum. How do we make sure that we have that common understanding that we can really use, even terms like superposition and entanglement, in a way that everyone fully understands exactly what that means, and how we can start to build towards that common set of knowledge that we can use to build our knowledge as a foundation to go forward in this quantum systems engineering field. What could it become? And that's where it's not just down to a couple of people in academia, it's a whole community industry response really to the challenges that we're looking to face. And the challenge to you all really as well is, how do we do more to push those systems engineering skills into academia and wider? How can systems engineering accelerate that development of anything that happens out of academia? Because fundamentally, it's not a core part, of how academia runs. There is no real basic SE tools that are used in academia as a standard. So there's an opportunity there to support and share and lean into those environments. So where physicists kind of traditionally use lab books, systems engineers use tools, processes, and ways of working. So the challenge is, how do we ensure that we're joining up and sharing those best practices to solve those complex problems? So how can you engage? That's the question to you all today. It might be re-engaging with your local university. It might be joining an encompassing working group or an encompassing UK outreach team, for example. It could be going to your local school and engaging with those low-level skills challenges, or it could be working with a university through one of the Royal Academy of Engineering schemes, through an encompassing UK initiative. It could be anything in the in-between. So I'm really keen to hear how you guys will engage.
Okay, folks, please join me in thanking Beth for her presentation. So who would like to begin?
Maybe I will note that any questions for Mark I will be taking away. I will not be attempting to answer any for Mark myself, but happy to take them and take them away.
On that same note, any questions that get put through to Slido, and whilst we're not necessarily facilitating it this afternoon's plenary session, any questions that get put through to Slido, we will try to pass those on to the presenters and get answers back, either via the website or back from the presenters to you.
Hiya, Beth. Thank you for the presentation. Manny Puri again for BA Systems. Scalability is obviously a big thing with quantum in trying to solve real-world problems. But have you seen any research done on the assurance piece, so like noise correction, error correction, to make sure that the end product that you're actually looking at has a value in it?
Yeah, well, actually, that is really the biggest challenge in quantum computers. So the challenge is not necessarily doing the quantumness itself. It's because it decoheres so quickly, we're having to error correct kind of constantly. So that is really the big challenge that the industry is facing in the quantum computer space. I don't think the other technologies, particularly sensing, hasn't really got that far in terms of understanding the insurance piece. Most of the work that's been done so far has kind of been very much at the academic funded level, so using kind of UK research and innovation money and grants. There's an example in Canada of a university using kind of the sensing capabilities to look at autism in brains, for example, but absolutely nothing really yet up that TRL stack to look at assurance. It's definitely an open problem that we've got to look at.
Who you are and where you come from?
Paul Davis, the systems engineer.uk, and also a visiting academic at Loughborough. I wrote the Dope Panic Guide to interface management, and you've just tempted me to throw the book in the bin, because step one is draw a system context diagram with a system boundary that separates the system of interest from the system context, including the interfacing system or interacting systems. Can't do that anymore, not with quantum technologies. So do you have any kind of mental image of what a system context diagram for involving quantum technology, because the system and its context are so intrinsically interlinked? Have you got any mental image of what that might look like?
Sure. So personally, no, but Mark is kind of absolutely working on it. So absolutely, that entanglement piece really puts a massive question mark over that system definition piece. And there is a chapter on quantum systems engineering in his book that's published this year, and it actually talks about an example of comparing the wave function both with the environment and without the environment. So the thinking is starting to be done, and we really need to make sure that brains like yours are in the conversation, absolutely, to make sure that we're starting to pull through the exactly so what of the solution. So I think that's the challenge. I think that's the position that we're at in.
Hello, Matt Windham from UCL. I'm interested in what engineers do in terms of both their individual activity and also as a community. And thinking about electronics, and this happened to electronics over the 20th century. It went from magic tricks or scientific papers, sometimes done by the same people, to individual crafts such as wiring up a valve in exactly the right way to do something, to a library of dependable components that engineers can put in system kind of architecture diagrams. So where do you think quantum is on that kind of spectrum? And is there anything that today's lot of engineers can learn from the 1930s grandfathers that did similar sorts of things?
Absolutely. I think that's a really, really brilliant kind of question and challenge. And that's where I think that's the opportunity. I think we need to maximise that experience. And exactly how we do that, I think, is an open question. And I'd appreciate maybe catching up kind of after that to look at actually practically what we can do. Whether it's potentially utilising the outreach group within ENCOSI UK. There's working groups across the world as well in terms of the ENCOSI kind of broad brush. But I think it's something that we need to invite more people into, invite more kind of thinking around, because like you say, the chances are it's definitely coming. This quantity fair is definitely coming. I think in terms of timescales, practically within the 5 to 10 years in terms of some of the smaller scale kind of sensing kind of opportunities. Quantum computers are unlikely to be able to they're not going to solve all our problems, but actually there are real implications in terms of what they can do. And if those quantum computers now that are in the hands of a couple of really big kind of businesses, and so what that means for going forward. So we do have some time, I think, which is maybe the key takeaway, but the time is now to start engaging and bring people in and preparing for the future for that to come.
Hi, Duncan Kemp, MOD and also another visiting academic at Loughborough University. Other universities do exist. You've talked about the systems engineering of systems with quantum in them, but I can reframe a lot of systems engineering problems as search problems, which means the whole quantum superposition could be used. So have we thought about what we could use in quantum technology to actually do better systems engineering at the kind of massive scale of do an n-squared grid of 1,000 things in it perfectly?
I mean, I think that's really another example of what I'm hoping to achieve from today, is that stimulation, is that, systems engineers, do not be afraid of quantum. There are opportunities to use it. It is not impossible to understand, and there are opportunities. So personally, not anything that I'm thinking about at the moment in terms of my current role, my current problem set, but absolutely the opportunities are out there. And exactly how we pull engineers in and give them that knowledge, there's lots of opportunities to engage. So what I would just say is that everyone who said they're a visiting professor, it is a normal thing to do. And it is completely possible and feasible. So if you're thinking maybe that's something I'd be interested in doing, do it, reach out, whether that's your local university, whether that's where you studied, or if you're not sure, engage with us as Encompassing UK, and we've got connections into those working groups and local groups as well.
Thank you. Jonathan Cashmore, Leonardo Electronics. I think it was in 2017, Catherine Stace did a presentation on biomedics, and there was an ecology that supported all of those. Is there an ecology for quantum? And how do you build one? Yeah,
and I think that's the real challenge that Mark and I are kind of posited in this paper, that doesn't exist. And I think we're starting from not a huge amount. It's still very much been an academic focus piece. And whilst there is some cross contamination within like the likes of IBM, for example, and Google, it's not something that is shared with people kind of broadly and widely. So I think there's an activity to work out, what oncology do they use, for example, in those big companies, and what can we be sharing and learning from broader. And again, potential there, that's the position of kind of Encozy at large, potentially to look at actually creating QSE as a thing has the potential to allow us to have a bit more of a say and authority, as Steve said today, on things like that. So as far as I'm aware, absolutely nothing yet, and I think it's a real good thing that we've got to get after.
Hi, Mark Ashforth, MOD. So I'm particularly keen on the threat to security and the opportunities in PNT, that kind of thing. But we've heard about these promises from quantum for a long time, and I wonder if it's a bit like controlled nuclear fusion, that it's always just a few years away. What's your confidence that we're going to realise those opportunities? Sure.
Well, I think the pathway of particular quantum computers, you can see the progress there. You can see the number of qubits that they're doing. So I think there's a real confidence there in terms of the growth of the capability. I think the position navigation and timing one is a really interesting one, because it is just so dependent on those exterior kind of environmental factors. So that's probably got slightly more of a question mark of exactly when and exactly how useful is it going to be. And it's a really interesting challenge of starting with what it is you want to achieve, and actually is there other way of achieving a GPS denied environment navigator. Quantum is an example of how we can solve it, and how do we put our energy into moving things forward that are likely, rather than fixating on a technology that we think that someone has a passion on to move it forward. So I guess a varying amount, and I guess the lower level sensing opportunities like the one in Canada are those examples of real actionable outputs of using quantum. So it's definitely on its way. The timescales in particular, we're not going to have a quantum feature in our pocket by next year. Let's put it that way. But the journey to getting towards really kind of broad brush technology is definitely something that it's worth us investing time in now, from my personal perspective.
Nathan Drury, Logic Consulting. Thank you for your presentation. Really, really enjoyed it. Very interesting topic. I suppose my question is around the MBSE piece. That's what I'm most interested in. Where do you see the key benefits being realised in the MBSE space? Is it pure computational power allowing linking of, say, machine learning into it, making it less of a person-intensive process, or what?
Yeah, I think the thing with MBSE is it joins together a couple of those problems and issues in terms of modelling what's going on, and then the scale element. And absolutely, there's opportunity in using kind of data solutions to help with that. And I think the so what is that ease. It's that joint understanding of what you can do, which will then hopefully lead to better interoperability, better assurance, better reliability, and better maintainability. So I think the opportunity is it's an example of how we can have that joint perspective on something, and it wraps in, the boundary issues, the hierarchical modelling issues, and helping academics understand MBSE better will only have kind of better knock-on effects as time goes on. So I think that's the opportunity in sharing MBSE a little bit more across the different communities.
Hi, Chris Haystackle of Arm Limited, previously of Teledyne E2V. When I was in that role, we did a number of quantum projects around quantum sensing and timing and those sorts of things. And at that time, to try and bridge that valley of death, there was government funding, Innovate UK, all of those sorts of things. I was just wondering what the current approach is to try and get across that valley. Industry isn't likely to invest large amounts of money unless they can see a profit at the end of it. I was just wondering what the current approach was to try and bring things out of academia and successfully into industry.
That's it. So it's still very much club funding. It's still very much UKRI kind of money. So within the last couple of years, huge amounts of money the UK government has kind of put up to progress these types of technologies. With that focus, on that security piece, on making sure we're that superpower, particularly in the UK, so that we've got those technologies being stimulated all the way through. And I guess this is the challenge, right? How do we, as a community, ensure we're supporting, with our kind of modelling minds and with that complexity solving aspect, so that it is an easier gap. Even if it's not necessarily with money, it's that joining and understanding and collaborating that can hopefully make us solve these problems a little bit better and a little bit quicker to get to where we need to get to.
Any more for any more? One at the front here. We'll make this the last one.
Deepa Ganesh from Kinetic. Thank you for your excellent presentation. I have a question. You mentioned about the quantum along with the systems engineering, but the major area on these days, we have many market available tools. Any particular tools you are working on now and the future? Could you suggest a couple of tools? Thank you.
Great question, and I think we're a little bit too early for that, I think. So there are obviously languages and tools that the academics kind of use, to go to create diagrams like that one I kind of showed earlier. So I think that's still to be confirmed. And I think, again, it's another great challenge of how do we have that coherent language, whether it's using linked data from our previous talk, for example, or whether it is, a whole new tool. So absolutely nothing that's really codified or set in stone yet.
They're giving you your slides back.
Oh, thank you. I was just going to say, there's obviously various languages that academics use to do their theoretical modelling, like that one. Oh dear. But yeah, there's not really any codified tools yet, and I think that's, again, another opportunity to collaborate and make sure that we're all aligned and happy with what it is that we choose to go forward with.
Okay, thank you very much, Beth. Please join me in thanking Beth again.
Thank you for listening.